Hello, here we are again. This is 105A video lecture 3. So let's get started. Taking it over to the undergrad room where I have twice as much board space. Let's see how that works out. All right, so what are we working on? We're investigating we had Newton's law for functions, for forces that are functions of position. And in that case, we were led to introduce the potential energy U of R minus F. Argument shows up here on F dot dr. I'm just going to write it that way. Some A to R. And so that's actually the compact form, but there's stuff going on in this integration that we had to investigate and we started doing last time. So where are we headed with this? Well, we have to prove that this potential energy really is a potential energy, and its gradient will give us minus F R. So the gradient of the potential energy will give us the force. We're going to prove that. And at that point, we're going to get energy conservation. R. So then we're going to have 1/2 m r dot squared plus U of R equals E, and which is supposed to be a constant. That's supposed to be conservation of energy. So we're going to work our way into that again, having already talked quite a bit about it. Work our way through to this point here, and then we'll have conservation of energy. We'll have a certain class of force vectors that satisfy all of these relations right here. Okay, so that's our start. Well, that's actually our goal, to talk about conservation of energy. Along the way, we have to investigate certain mathematical topics. Okay, and so I'll put a little list of the math topics that we want to cover in order to make everything here clear and rigorous. And the first one is the chain rule for multivariable functions. Multivariable functions. So we have to talk about the chain rule. From there we can get into divergence, gradient, curl a bit. And so in other words, derivatives of multivariable objects, and then integral theorems. And having gone through that, then we'll be able to return to this thing and get everything squared away neatly. Good. And the integral theorem, of course, is motivated by this thing here. We talked last time about how this is really defined, what's it really defined as. This is just, symbolically we had, here's a point A in space, we're going to integrate along some path to some point R in space. That's what's going on right here. So we'll look a little closer at all of these things. Good, so let's start with the chain rule for multivariable functions. This is something that is used quite a bit in mechanics, more next semester than this semester, but it's time to talk about it. So suppose we have a function, okay, so we're doing this chain rule first. Suppose we have f equal f of x1 of t all the way out to xn of t, okay? And this is just a scalar function. This is the vector valued argument here. And of course, an example f of r of t, where then we would have x, y, z, or x1, x2, x3. But everything we're doing holds for more variables as well, okay? Yeah. So if we want to take the time derivative, and this course doesn't have to be time, it's just a parameter, but we're doing physics, we'll use the time often. So what is this time derivative here? It is the sum of all of the individual chain rules. So if this were a one variable function, we would just say we have the derivative of f with respect to x of 1, okay? And then we'd say dx of 1 dt. Okay, so 1 and 1, but of course it's not just a 1, it's 1 through n. So I'm going to call this 1 here I, and sum over from I equals 1 to n. Okay? And you could write these out from 1 to 3 if you had x, y, and z, or more if you have more variables. And this f here is, of course, evaluated at its argument. I could have written this, you have bad form, I'll erase right here. So we would have df of, now, since this is x1 to xn, I'll just say x vector of t, and then dx of I. Once again, summing over all of these from 1 to n. Okay, let's keep looking at that. So we're looking at this expression here. We can also look at it in the following way. Just kind of a summation over these individual components. We could say that was the gradient of f of x, n-dimensional gradient if you want, or just think of the 3 variables, no big deal, dotted into dx dt. The dot product, the scalar product, the summation over the product of those components. Okay? This gives it a more geometrical look. Okay? And you can see the reason for this rule is that the derivative is, in general, the linearization of a function. So this is the linearization of a function of many variables. This kind of a dot product, and the sum, that's a linear mapping. Okay, good. So there we have df dt. That's the chain rule. So something we really need to think about, or need to be able to use. Good. So we've taken care of this. We'll get some practice on that coming up soon. What about divergence, gradient, and curl? Let's start with the gradient since we have it in front of us. Gradient of f, or gradient of f. What we want to know about that right here, it is df dx of 1 df dx of n. It's a vector. So the gradient takes a scalar into a vector. Grad turns scalar into a vector. Okay. What about the divergence? Divergence is always the divergence of a vector. Divergence of f equals df1 dx1 df2 dx2 plus df3 dx3. So good. We've seen that before. Definition. And what we're driving at here is that divergence turns a vector into a scalar and finally I'll say a word or two about curl. So 3 curl of f, also referred to as curl of f like that, and we can write curl of f in that formal determinant method, which is just a good way to memorize it. You've got your I, J, K, your derivative d dx, d dy, dz operating on f, x, fy, fz. Okay, so write that down. I don't know if that's legible right there. You've seen that before, so curl takes vector into a vector. So I have some great examples of these coming up that are very germane to everything that we're doing. Okay, so we talked about chain rule, and we just did a quick review of these vector derivatives, okay, vector differentiations. Now I want to spend a little more time than just this on the vector theorems. Okay. The integral theorems, they play a big role in theoretical physics, and more often you're just using them in your proofs more often than you're actually evaluating one explicitly. At least in this class. Let's say it's 50-50, but you're not necessarily setting up difficult vector integrals as much as you're manipulating them. Good. So, integral theorems. I'm going to start with the easiest, most basic one, and in a sense there is only one integral theorem. So this is the way we look at this subject. So the basic integral theorem, I should give this one a star, is just none other than this one, f of b minus f of a. Okay. Integral over the derivative. Fundamental theorem of calculus in something, right? This is a search for the antiderivative. Call it what you want. Okay. What's going on here, this is what we want to spend a little time thinking about. We've got a function, our x-axis, okay, here's a to b, and we're replacing the, integral of its derivative by the value of the base function at the two endpoints. That's the key right here. We're replacing this integral of a derivative by the value of the function at its endpoints. That's the theme that's going to repeat itself with the other integral theorems. Okay. So this is why this one is worth showing the proof in scare quotes, proof idea, and that is the following. Over here, very loosely, I have a derivative, so I have f of x I plus 1 minus f of x of I divided by x I plus 1 minus x of I. So you can see x I plus 1 minus x I equals whatever, okay? We're going from A to B, and we've broken this up into enough of these. Yeah, so we're looking at a Riemann sum. Well, this was the derivative in the limit of many I, and this is the dx. Okay. These are identical, and what you're ending up with is a cancellation of these. I plus 1 minus I, as you go along, you're always subtracting off the next one till you end up with f of x of, I'm going to call this I maximum, largest I, minus f x of I minimum. Whatever whatever indices I had right here, these are the two endpoints. So that's a trivial proof, right? Trivial as can be. And in fact, the proofs of the more complicated integral theorems always go back to an idea just like this one. Okay? You can actually do them by hand like this if you're interested. Sometimes I do it, but we may not have time. You can play around with that yourself. I'll indicate what those proofs are as we go through. Okay, so that is the most important of the integral theorems I'm claiming. Okay. The next one, maybe I should number these instead. The next one, put up here, is the integral now from A to B of the gradient of f dot dr. Okay, so that's the one that got us onto the whole subject in the first place. That's simply that's the form of our potential energy integral. Okay. And so what is this? This is a chance for us to do a little bit, refer back to the notes from last time if you want. So we would need a parametrization, and then we would have gradient of f of r of tau, and that would be dotted into dr d tau, and then would be integrated over tau. So that would be when you actually have a parametrization. I would have to say I've got a tau sub A and a tau sub B. All shenanigans here. So that's the symbolic form. This is how it's actually calculated. Now we just did our chain rule. So in your notes on the chain rule, what we can see is this thing here, tau A, tau B, this is just d over d tau of f of r of tau. D tau. That's what this is, previous by the previous board. And yeah, now we're back to this integral right here. So this is f of r of tau sub b minus f of r of tau sub a. And I'm going to go ahead and erase what I have down here. One more step. See, we reduced this one to the one I had here previously, and this is f of b minus f of a. So there's our integral theorem. This equal to that. And again, same picture as I had earlier. You got some point A in space, and you're going along some curve to some point B in space. Okay. Good. So there's our second integral theorem, and it was the gradient of the function integrated along a path is equal to the function at the endpoints of the path. So integrated along this path here, replace it by the endpoint values at the endpoints. Okay, so that was in fact this one again, as advertised, slightly different form. Now let's do the next one. And now I'm not going to prove these. I could, my rudimentary Riemann sum proof. I find those to be pretty fun. But the next one here, number 3, this would be Stokes' integral theorem. So how do you remember these things if you're just trying to pull them out of your memory? Well, you remember them by what I just had there. It's the integral over a derivative, in this case, the curl of a vector field. And this is going to be dotted into a surface normal. I'm going to call that area integral, a surface integral, so there's an area. See, so that's the integral over the derivative equal to the value of the function on the boundary. Just like over there, the value on the boundary was at the endpoints. Here, the boundary of a surface. Now, there's your surface, so the value of the, or the boundary of this surface is a closed curve. So, that's the integral f dot ds, I'll call it, length element, f dot ds on the boundary. I think this is a nice nomenclature that we get from the mathematicians. This del just represents the boundary of this set here. So this is an area, so this is the boundary of it. Okay, oriented closed curve. Okay, whatever. Good, so there's Stokes' integral theorem. And this is the one we need, so we're going to hold on to this one. This is the one we need for our central force, or for our potential energy problem. Finally, I'll just write down Gauss's integral theorem. And that would be, so again, the integral over a derivative, so this time it's the divergence f dot volume, so I'll call d3r, that's a volume, and we'll say it's integrated over volume, and that's equal to the value of the function on the boundary. Once again, it's like the value of the endpoints. So in this case, it would be the integral of f dotted into the surface normal, the area integral on the boundary of the volume. That's the surface that bounds the volume. Okay. But you see what theme I'm getting at. It's always an integral theorem. You've got the derivative here, and then you've got the boundary on the right side. Good. So that's an interesting discussion of integral theorems. What I like to do sometimes is actually just do a crude Riemann sum version of these things on a grid. So for this one, if you were to do this proof, you would break up, what should I do here? Let me erase a little. Okay, so let's call this proof idea for Stokes. You guys may want to do this on a rainy day. Okay. Proof idea for Stokes is that you imagine you've got your area here, and you can just choose a square, and you break it down into some cells, and then you evaluate these vectors dotted into n hat. In fact, if this is your xy plane, and then your n hat is in the z direction, so you're doing it on a two-dimensional version. Okay, and you just evaluate the derivatives here. And what you will find is that they are equal to the value of the right side as interpreted going around this thing counterclockwise. That's what you'll find. Evaluate the derivatives, and then you say, well, an integral, I just for the whole thing, I'm just going to sum them all up, and each of these cells that abut each other, they get a cancellation. And then this one gets a cancellation here. This one's going up, this one's going down. So what you find is an analogy to that Riemann sum that I had there, or pretty much the two-dimensional version of it. And you do something similar for Gauss's integral theorem as well. You literally write down what these things mean, kind of in a Riemann sum form on some cell. For Gauss, it would be on a cube. So this would be for Stokes. For Gauss, you define a little cube in XYZ space. And again, you're going to find the divergence over the volume of this cube is going to be equal to these 6 area integrals that comprise the 6 sides that a cube has. Okay, enough of that. I'm just putting that up there if you're interested in playing around with that. It gives you a lot of understanding, actually. Okay, but we're back to Stokes and his integral theorem with regards to our potential energy functions. So I'll go ahead and leave Stokes up here and clear up some space. Actually, maybe I'll take Stokes away as well. Let's say back to the problem at hand. Yeah, let's do it this way. For our force f of r, force vector that we're considering, we would write with an arbitrary surface, what we write is surface A. The curl of F dot n at dA, surface A, is equal to F dot. Now I'm going to use dr on the boundary of A. And again, here's an arbitrary surface in space. Actually, probably shouldn't have a cusp there. Arbitrary surface in space. There's the boundary of the surface. There's the surface. Going into the boundary. The surface normally, you know, is sticking out here somewhere. Yeah, surface normal. Yeah, what are we looking at now? Last time, we wanted a closed integral to vanish. In order to have a well-defined potential energy, we need this closed integral to vanish. Must equal 0 in order to have well-defined potential energy. Okay, that's what we have on the right side. What do we have on the left side? This can always be 0, and this is an arbitrary surface. That's only going to happen if the curl of F is 0. Okay. So 0, regardless of what curve we choose. Therefore, regardless of what surface and its orientation. So therefore, because of this implies that curl of F has to equal 0. So yeah, curl of F equals 0. Okay. So there we have it. A potential energy function is well defined if the integral over this force is independent of path. That's what it means for the closed integral to be 0. And that's going to be the case when the curl of this function f vanishes. So I'm going to give us some examples of a field, force field we'll call it, whose curl doesn't vanish, as well as one that whose field does vanish, whose curl does vanish. And those will be the homework problems. Good way to get the board set up for some next week's homework problems. Maybe this week, we're not sure. Let's see here. Okay, so here's what I'm going to do. I'm going to set up the homework problems I had in mind and get us started on them, and then we'll go back to what we started talking about, conservation of energy. This was a bit of a detour, but a necessary detour. Okay, so let me write down a couple of homework problems that you'll actually find interesting. And these are vector differentiations. So homework I gotta decide when they're due, but let's put them up on the board first. So calculate gradient of R, the gradient of f of R, and the divergence of the gradient of f of R, where this R is equal to the magnitude of R, or we can write x squared plus y squared plus z squared. When we're going through with these, it can be helpful to take the magnitude of R to equal square root of x1 squared, x2 squared plus x3 squared, if we're going to use some kind of index notation. Yeah, so that's what we want. And I'm going to start with this one, gradient of R. Okay. And then you guys can carry on with the other one. So for the gradient of R, we're looking for d over dx of, you know what, I'm going to do this in indices. d over dx of I, x1 squared plus x2 squared plus x3 squared to the 1/2 power. Okay. We get the ith component here, then we've got all of them, right? I equals 1, 2, 3. So what do we have here? We have 1/2 times this thing to the negative 1/2 times the inner derivative, doing the chain rule now, 2x of I. Of these three, we pick the ith one, 1, 2, or 3, pick the ith one, 2x of I, these cancel, and what we end up with is x of I divided by this, right, minus 1/2, so x of I divided by R. Okay. X of I divided by R. So the gradient of R, go through this calculation of x of I over R. What that means is that for all three of them, which is the gradient is proper, it's R divided by R. So this is something you should do a few times, and then you should know it. You don't have to keep doing this calculation, because it, once you know this, when you do this problem, you're going to have a chain rule. It's going to give you a really typical result. This one here is going to be a little more interesting. So this one I've taken care of. This one you also want to get in a very compact shape, right? The gradient of R is the unit vector pointing away from the origin. That's what that is. Now for this, I'll just put this as a note as well. When you're doing this divergence of the gradient of f of r, that is d dx of d f of r dx plus d dy df of r dy. So I'm not doing the indices this time. You can nail this with the indices as well. Plus d dz df of r dz. So you got a couple more steps left, and then you get a very interesting result here. It's even more interesting if instead of a three-dimensional vector, you take this r with x1 squared to xn squared. And you get a general result in n space. Maybe we'll tackle that one later. For now, we'll just do it in three space. Okay, so there's one of your homework problems. Right there, we got a good start on it. The other one is even better. Okay, let's write this down. So we've got this here, erase this. So the next homework problem is calculate the curl of, well, let me, curl of f, where f of r equals minus alpha over r squared r over r. Yeah, that's going to be Newton's law or Coulomb's law. Okay, so that curl's got to vanish or else we're in trouble. Okay, but go ahead and calculate it explicitly. You've got, because there's enough going on here, okay, you've got this vector with its three components, right? I'll just put a note here. Fx of r is equal to minus alpha x over r cubed. R, of course, as before. And then Fy, as said, I'll just do Fy as well. So see what's going on. Minus alpha y over r cubed, etc. Okay, calculate the curl of this. It had better be 0, but you know, you lovingly take all those derivatives. Okay. Now here's the best problem. The best one is the curl of an interesting vector field. So, last problem, let f of r equal b k hat, let me erase this stuff here in the way. B k hat cross r over r to the n with x, y, z, right? K hat is in this direction. And our vectors are just going to be two-dimensional vectors, x, y, and 0. Okay. So what is this? What would this be? Because we want to calculate its curl. So if you you take the cross product, say here's a vector for us, take the cross product, let's put a top view here. Top view, we've got x, y, z pointing out of the board. This k hat is the one we're talking about there. K hat cross any vector is in that direction. What this describes is a circulating vortex, actually. And if this n were equal to 0, in other words, if we just had the numerator, then this would just be a circular motion. Okay. K cross R would just be circular motion like a rotating bucket. This could be a field like a rotating bucket. But because it's decaying here with this general power n, there's some interesting cases here. Generally, there is a curl. There's actually there's a value of n for which the curl vanishes. And that's pretty interesting as well. This is the kind of thing you run into in fluid mechanics and in 107, okay, electricity and magnetism. And really, these central type of fields and these circulating type of fields are the two primary types of vector fields. That's what we can break them down to. Good. So let's so and so and so and so calculate the curl of this vector field here. This one's going to vanish. This one's going to be more interesting. We have a general n dependence here, so that's also interesting. Okay. So that's just some good differentiation on interesting objects type of calculation. Okay, now we're going to wrap things up with our conservation of energy, what we started out with. This was a long and necessary detour. So now we're back to the force, function of R. Notice these two homework examples are forces that are functions of R, so they're germane. So right here, finally, back to Newton's law, F of R, okay, with curl of F equals 0. Okay, now we're in business. We've got minus integral R with gradient U of R equals minus F of R. So all these results have now been secured, and m R dot squared plus U of R is equal to E. So it just remains for us to prove this thing, energy conservation. It remains for us to prove that, and then we can go back to our homework problems and say which ones of those forces can have the potential energy function, which we'll then know. Okay, so how do we prove this? Proof. Well, we know that if this is a constant, then its complete time derivative vanishes, so we're just going to take the time derivative of this left side of the equation. So d over dt of 1/2 m. Now this r dot squared expanded out is x dot squared plus y dot squared plus z dot squared. And this u of r, I'm just going to write x and y and z. Good. Time derivative 1/2 mx dot squared turns into 1/2 m 2x dot x double dot. So the 2's cancel, n x dot x second derivative. Same thing, m y dot y second derivative, and z dot z second derivative, plus, okay, running out of room. What about the proof right here? The page is not running out. Plus du dx x dot. Now I'm applying the chain rule to this multivariable function. Du dy y dot plus du dz z dot. So here I did this chain rule here. Here I did the chain rule to the u, working uphill. Yeah, this is the crucial step. I'm just going to give myself enough room. What you have here is apparently a scalar product, because x dot x double dot y double dot z double dot, that's a scalar product between the velocity and the acceleration. So I can pull out the velocity, and I have a scalar product with mass times the acceleration. Okay, that's that dot product there, so that was crucial. What about here? Here I have the scalar product between the gradient and the velocity. So that would be the velocity scalar product pulled out here, common factor, and I have plus the gradient of u. Working up here equals, what is this? This is Newton's law. Minus f. Zero. That's just Newton's law, so that equals 0. So the derivative here equals 0, therefore E is constant. So what do we get out of all of this? We got the necessary formalism to talk about dynamics in 3 dimensions, and we got this, of course, most useful result, conservation of energy. First integral, same as in the one-dimensional case, only a lot richer. Yeah. That will be a good place to stop this. Let's see while we wrap this up now. So, yeah, we've got conservation of energy. Let me write down a couple more words where we're headed with this. And where we are headed next, central forces. Central force problem. That's our big goal for this semester, right? We have to nail that, and we will. So yeah, central forces I've set up pretty well, because a central force is the following. Central force for one particle, you've got your force as a function of position. It has the form a magnitude here is a function of position and a direction. So this is just the unit vector pointing away from the origin, and that's what is essential force with respect to the origin. Okay. So Newton's law would be M equals F of R. So that's the general situation that we're going to be working with. And you'll see in your homework, among other things, actually maybe we should have formulated a little more general, but yeah, this is by definition curl-free, or if you calculate it, you'll definitely know it's curl-free, and therefore it has potential energy. So that's what we're going to do. We're going to take these central force things, potential energy function, and work our way through the interesting formalism. Okay, that's long enough for today. I'm going to call it, and next time we'll just get to work on this. Okay, away we go.